Hello, welcome everyone. Thanks for joining our diagnostic training session today. Now, this is a pre-recorded session this week, so if you do have any questions and you're joining us on Zoom, just reply to the confirmation email that you got from Zoom, and I'll be able to reply to those. If you're watching us on YouTube, just leave a comment underneath, and I'll try to get back to those when I get back. And on Facebook, same thing, leave a comment underneath the video, and I'll get to those when I'm able. So my name is Jason Gabrinas. I'm one of Snap-on's National Diagnostic Technical Trainers. Been in the training department the last 9 years or so, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep with Snap-on. Got about 30 different Snap-on franchisees I worked with, as well as the shops that they serviced in order to help everyone get the most out of their diagnostic needs. Then before that, it was 8 years at Subaru. So over time, working at the dealership just ended up becoming the default Diag guy, I guess. So always ended up with the drivability problems, the intermittent problems, weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth and learned a lot about diagnosing vehicles. And before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So our topic today is talking about component testing in general. How if we're missing out on component testing, if we're not testing components, or not testing them properly, then we're missing out on a bunch of our information when it comes to diagnosing a vehicle, especially nowadays, considering parts situations with supply chains and just part quality in general. We want to make extra sure that what we're replacing is in fact bad. And then when we do replace it, we want to make extra sure that it's going to solve the problem. And that's not, the car's not going to come back. So we want to make sure we're going to solve both of those problems. And that a lot of that's going to be by components. So if we think about diagnostic tools, we have two different types of tools. We got more than that, but the two main tools that we use are going to be scanners and scopes. Scanners are going to point you in the right direction. It's a good compass. It's going to show you where you need to look, where you need to go, but it's really only giving you part of the equation. As we said, we only have half of that. It's the effect. The effect's going to be after it already happened. So we want to be able to find the cause to that effect. And that's where a scope comes in, or a component testing portion of our testing is going to come in. So if we think about a vehicle's computer, let's think of it like a house. It's got a front door and it's got a back door. So on the front door, all my inputs are going to come into the computer. So my NOx sensor, my oxygen sensor, my cam and crank sensor, all of those inputs go into the PCM. The PCM then processes that information however it's programmed to do so. And that's the key right there. Because the computer is only as good as its programming, and that's why we have these things called TSBs, reflashes, recalls, things of that nature, reflashes especially, because the computer wasn't programmed right, and they said, oops, we need to fix that. So they'll put out a bullet and say, hey, you need to reflash. After it does its processing, though, it sends the information back out the back door to the scanner. So if I'm reading just the data with the scanner, I'm only looking at half of that equation. I'm looking at the PCM's interpretation of the data coming in based on its programming. So you could be led astray on occasion. There's multiple reasons why that happens, but don't blame it on the scan tool. A good friend of mine says, scan tools don't lie, they get lied to. Right? So the scan tools only could be as good enough as the information coming out of the computer as well. So you can't 100% rely on just the scanner data, especially if you have a drivability problem with the car. So we want to make sure we're verifying our problems, verifying the issues that we have. So since we have two different types of signals, means we need two different types of diagnostic tools. So anything coming in the front door there, it's going to be our raw data at the component level coming into the computer. We need something with a scope or component testing in order to test that. And then, of course, to get the back door, the effect after it already happened, we're going to need something with a scan tool. Some scan tools are separate. Some scan tools are integrated with a guided component tester or a scope, as it were. So just depending on what you have for a tool, you need the right tool for the job. And you might be thinking, well, why don't just rely on the data? Why not just the computer's telling me what it's thinking? Well, it's not always, as we said, 100% correct. Back in the day, back when we first came out with scan tools, late 80s, early 90s, OBD1 vehicle, that data stream coming out of that car, you might have 5 or 6 different data points because there wasn't a whole lot going on. You have maybe 5, 6 sensors, not a lot of data there. And if you're lucky, and you saw that data on the screen, if you're lucky, it might change every couple seconds. because the data refresh rate on the car wasn't all that fast. And granted, the tool didn't have to be all that fast either. But nowadays, I'll tell you, data overload is going on here. We have these rolling computers going down the road. So these digital readings, the multitude of sensors we have, the multitude of data that we have coming out of that computer, those digital readings can be changed in 10 times a second or faster. I don't know about you, but I have a really hard time reading something when it's changing on the screen 10 times a second or faster. And it's just way too much. There's 400, 500, 600 PIDs that you got to scroll through in order to find what you're looking for. Of course, we have ways to cope with that with custom data lists and things of that nature. But just look at that, 10 times a second or faster. Valuable data, but it's often too fast and too much to comprehend what's going on. So it's not always scan data. Graphing the data is better. So we can take those numbers and graph them as a recorded history. That's what the graphs are. Graph them at a recorded history over time of that information. That's useful for seeing trends. Are things getting better? Are things getting worse? Are things just completely kaput? Also, there are some things that you can only see looking at data. There's things that occur inside the computer, the calculations that it makes, like misfire counts. Some of the AF sensor readings are done within the computer as well. So you do need that data. It's not like you just don't use it at all, but it's just a piece of the puzzle. And I see somebody just chimed in. Chris said, just because it's new doesn't mean it's good. Exactly. So we need to make sure we're testing the part. Test the part first. Let me give you an example. Top part of the screen here, that's processed data coming out the back of the computer, hooked up to the OBD2 port, right? Reading oxygen sensor voltage coming out the back of the computer. This window right here is a scope looking at the same oxygen sensor, reading the same data at the same time. It's reading the voltage. But these two red boxes show the same amount of time passing. I think you'd agree there's a huge difference in these two patterns. And a lot of that has to do with the refresh rate. If you think about the scan tool is going to send out the signal. It's going to measure the signal first. Measure the signal, calculate it, send it to the scan tool. Measure it, calculate it, send it into the scan tool. All of that takes a little bit of time. It's milliseconds, microseconds, but it takes a little bit of time to take that in, do the calculation, and send it out. So due to that, you're going to miss some information. Versus if I'm hooked up directly to the component itself, reading the voltage that's coming off the component before it even gets to the computer, I can see that raw data before the computer gets its grubby little hands over it. So if I was just relying on the scanner data, I wouldn't have seen those two little dropouts in the voltage. Now, it might not necessarily be a bad thing. It might be okay, but I didn't even get the opportunity to see it by looking at that scanner data. So that's why we need to have both tools in our arsenal. We need to have a high sample rate scope to be able to capture. So we talk about scopes and component testing and testing components. And why do I need to use a scope? There are other ways to test things. We can test voltage, we can test continuity and all that. And a lot of times that's what the manufacturers want you to do. But being able to visually see a picture going across the screen that represents what's going on inside whatever the component is, in my mind, that's a lot easier to kind of see once you understand what you're interpreting. So what is a scope anyways? So I think a scope, when I like to think of it, I think of it as a window. The window I'm going to look through and I'm going to see what is this component doing electrically, mechanically, however I'm measuring. What's it doing? And when we're changing the scale and the sweep and the settings on the scope, all we're really doing is changing the size of the window. Am I making it take up more of the screen? Am I making it take up less of the screen? Am I looking at more time passing or less time passing, right? So it's a measurement over a period of time. And that's all it really is. So I know some people think scopes are scary and I'm going to break the car if I'm working on it. You don't need to worry about it. All you're really doing is looking at the voltage or the pressure or the current or whatever I'm measuring through this window to see what you're looking at. So component testing really helps us, and I see a lot of good back and forth going up on YouTube right now on the chat. Comebacks and intermittents. Comebacks and intermittents, in my mind, are the two 4-letter words in the industry, right? I hate comebacks and I hate intermittent problems because they're a royal pain to diagnose. So it's always good to verify, and then maybe verify again. So remember, the scan tool only shows us the effect of the problem after it already happened. It's a good clue. It's going to point us in the right direction. It's going to show us where we need to go, but it's still only the effect. We want to verify the problem and verify the repair after the fact. Let me give you a little, for instance. Get a vehicle that comes in. Got a P0102 mass airflow sensor, right? Pull out the flow chart, look through it, measure a couple things, whatever the OEM tells you to do according to the flow chart. And then you say, well, I guess it must need a mass airflow sensor. So you call a parts store. Call a parts store and say, hey, I need a mass airflow sensor for XYZ vehicle. And they say, okay, maybe they have it in stock, especially nowadays, right? Maybe I have it in stock. Maybe they don't have it in stock. Well, let's say they do have it in stock in this case, and you can get it, and it's like $300. Part comes in. Before that car leaves your bay, you want to double check and test that part before it leaves. Because how many times have you gotten a brand new part in a box that didn't work? Happens all the time, twice on Thursday. So we want to make sure that we're verifying the part has indeed failed. We can be a lot more confident ordering it. And then we also want to be able to verify that the part fixed the problem and it's going to be able to go down the road and not give us that comeback, that boomerang car. So we want to verify the problem, verify afterwards, make sure that that is not going to cause a problem. Right? When it comes to component failure, when we're testing these things, what are we really looking for? In my mind, it falls into these three different buckets. So we either have an open, we have a short, or we have a resistance problem. So an open is going to be, it could be either way. It could be I'm getting no voltage to the component, so the voltage supply is not making it there, or I'm not getting any voltage from the component. The power supply is making it to the component, but the component's not letting anything out. In that case, it's open. Or a short. I could have a short to power, so excess voltage, so it's supposed to be 5 volts and I'm getting 12 volts, that's a problem. Or insufficient voltage. If it's shorted to ground, and maybe it's pulling some of the voltage away, but not all the voltage away. It's supposed to be 5 volts, now we're seeing like 2 volts. And then that also goes hand in hand with resistance. Corrosion or damage to a wire, we might not be able to pass through as much voltage or current through that wire as we need to. I always give the instance of, let's think about a multi-stranded battery cable to the starter, right? Battery to the starter cable. It's got a couple 100, 300 little copper strands in it. And if I were to use an ohm meter on that and I were to measure and see what the resistance is on that, on just a normal, let's assume it's okay, multi-stranded wire, what are we going to see for a resistance? Well, it's probably going to be just open, zero resistance, because it's just a straight circuit. It's good. Now, what if I were to take one little strand of copper out of that multi-stranded copper wire and measure on either sides too? It's going to give me about the same reading, I would say, because it should have the same lack of resistance because it's going through there. But will that little tiny thin strand of wire start a vehicle? It's not going to carry enough current. It's going to get really hot. It's probably going to melt. So we need to make sure that we are testing multiple ways and not just relying on the ohm meter as well. So we're going to test for open, short, or resistance. So here's an interesting case study that we came across. So on an 05 Jeep Wrangler, kind of looked like this as well, had the big tires and the lift kit and all that. And the person who owned it did a lot of off-roading and things. And they came across a problem one day where it would crank and no start. Would crank, just wouldn't fire, wouldn't start. So they went to the internet and asked the internet forums, hey, what do you think this problem is? And they said, well, replace the cam sensor and the crank sensor. That's got to be it, right? So we're just going to do our shotgun approach and we're just going to replace parts because the internet told us so. But it's in the shop now. The customer had already attempted some repairs, and that was their repairs they tried. They tried the cam sensor, the crank sensor, didn't fix the problem. So where are we going to start? Well, the first thing we want to do is see, are there any codes in it, right? So first thing we want to do on any diagnosis, if the car has the capability, which most of them do, but we want to scan the vehicle. So we'll go in, do a code scan through all the modules, and no codes in this case. So it's a no start, crank but no start, no codes though. So where do I go next? So on the Windows-based tools that we have, and actually on the non-Windows-based tools now as well, each of these underlying modules is a link. I can click on that engine and that'll bring me into the engine module, so I don't have to back out, find it on the list and all that. So I can go back into the engine. Next thing we want to do is, on a lot of vehicles, this has been there for quite a while, Troubleshooter is in there. And that is a key resource that you can use as well, especially when you don't have any codes to go on. So if we go into Troubleshooter, we'll see we got code tips, symptom tips, time savers, test and procedures, A lot of information in there. It's going to tell you about the vehicle, but one that not on every vehicle, but if you do find it in there, it's called fast track data scan. This is going to help us interpret scanner data. There always seems to be a lot of confusion about that, what scanner data is and what it means and what's available. So you can see a list of data on here. Some oxygen sensors, intake air, idle air control, and so on. But I see this one over here, cam sync cam sensor status. So we already know the customer replaced the cam and crank sensor. And we also already know that it could be bad, it could be faulty, it could have just done it and it been a faulty sensor as well. But cam sync cam sensor status. So let's go in there. So this is going to tell us about it. What does it mean and what do we have for data? So it's actually going to give you scan tool data in here. So the definition is, does the PCM see the cam and crank signals during startup and normal operation? It is a yes or no pin. So went in there, cranked it over, crank. No. Never changed. So according to the processed data, we talked about that before. According to the scanner data, it doesn't see the cam and crank sensor. I said, all right, let's go back to the home screen. Now, the shop I was working at, they were going through the factory trouble chart. And you're working at Subaru, as I did, you learn very quickly that the manufacturer's flow charts aren't exactly the best in the real world all the time. I'm sure some manufacturers are better than others, but I do remember an instance at Subaru where the car was throwing a cam sensor code. And not one place in that entire flow chart did the manufacturer say, hey, look at it, take it out, test it, replace it, none of that. So according to Subaru, a cam sensor code could not be possibly caused by a cam sensor. It had to be something else. So I learned really quick that maybe we want to figure out what they're trying to do and test it first. Just go right to the part that we're sniffing up that tree, and then let's just try and fix that part. So going through the flow chart on this code for this vehicle, or no, we didn't have a code, so it was a crank no start. On crank no start, going through the flow chart, it takes 14 steps before it finally says test the thing. So why don't we just test the thing first? Take out all that middleman, take out all that time, and just go right to the part and see if it works. So the easiest way to do that on this tool, since it has guided component tests, we're going to go into guided component. And you can see there's many different categories of stuff in here. So we have ABS, body electrical, charging system, etc. Cam and crank sensor, of course, will be under engine, so we'll go in there. You can see all the different components in the engine and also the subsystems that we can test. So the first one we want to do is crank sensor. First thing is we can always read component information, but in this case, I want to do a signature test because I want to see what can I see with the signature. So if you hook up and look at the signature, you can tell a lot about what's going on. So go into a signature test. Now it tells us we're going to back probe right here on the crank sensor. This is the crank sensor lifted up in the air. We're going to back probe on this wire. So if we go into yellow is the crank signal, black's to a known good ground. So yellow is that signal right there, and that's where we had a back probe, black to a known good ground. And I didn't take a screenshot with the known good in there, but there is a known good pattern in the tool for this as well, and this matched it perfect. Cranked it over, got a bunch of pulses, then a low wide pulse, and then a bunch of pulses, then a high wide pulse, and so on and so forth. As it was cranking over. So testing it at the component, that means that the component is good. It's getting power, it's creating signal. Let's do the same thing for the cam sensor. Go to the cam sensor, back probe it there. This one I did capture the known good pattern. So the pattern should show 321, 312 on the pulse. 321, 312, 321, 312. And you see how they're getting spaced further apart because it was slowing down as the battery was wearing down. But crank. And we can see 321, 312, and so on and so forth. So we know the cam sensor was good. Crank sensor tested good, cam sensor tested good. What's next? Let's verify that the signal's making it back to the computer. So we tested it at the computer. We back probed there, checked on the crank sensor, looks good. Checked on the cam sensor, 321, 312, looks good there. So we established the cam sensor and the crank sensor are both working the way they're supposed to. We also verified the signal are getting to the PCM. So we just verified the harness is good all the way back, signal wire. Because it's outputting a signal there, it's outputting a signal there. The signals are getting to the PCM, and the PCM is not seeing the signals from the sensors because we looked at that data to help us. And the computer said, well, I don't see them. They're not there. I don't see them. They're just not there. So the signal path is good all the way up. The components are good. So that must mean this thing needs a new PCM. They replaced the PCM, set it up, fired right up. Now, they were curious, the shop. So they said, all right, let's take the computer apart and check it out. And sure enough, had some bad solder joints on those two. They're right next to each other. The cam and the crank, they're right next to each other. So that's some bad solder joints on there. So that was the problem. And they just wasn't making contact. But had we only relied on the scanner data and nothing else, we hadn't tested the components and we looked at the scanner data and said, oh, I don't see the cam and crank sensors. Would you have maybe thrown another set of cam and crank sensors at it? Possible. How long would it have taken to arrive at the same conclusion that we did, that they were good, it's just the computer was bad? That probably took 15, 20 minutes putting the thing up and down in the air. Got to check pin fitment as well, like Chris just said. But how many hours would it have taken to arrive at that same conclusion without any other problems? So that's why we test. That's why we test. Because the scan tool can only tell you so much. So we talk about guided component test. What is it and how does it help us? Well, it's inside any snap-on scan tool with a scope. So think Modus, Triton, Zeus, Ferris, Vantage. All of those have guided component tests. And even if you're really good at using a scope, I still recommend using a guided component test because we don't know everything about everything on every car. But there's a nice database of over 5 million guided component tests. And it gives us operations, locations, connector views, tech notes, and between 1 and 6 testing methods from low amp probe testing, analog testing, digital testing, secondary ignition testing, pressure testing even. Any of those things can be in there. By doing this and using this can help us avoid unnecessary parts replacement, as we already discussed. We don't want to replace a part that's not bad. In turn, that'll help prevent comebacks, which is a good thing, or at least lessen comebacks. Every once in a while, you're still going to get, but it's going to help us nail those down so we don't have to do it. It's going to help prevent comebacks, which will also prevent the loss of a customer, because what's worse than a comeback? It's a never comeback. And what's a never comeback? A never comeback is, well, you didn't fix it. They had the same problem, so they went somewhere else. Said, well, maybe they can fix it. And sure enough, maybe they do fix it. So what happens with that? Then you lose that customer and they end up becoming a customer of that other shop. Flip side of that, though, if you're the shop in town that does the testing, the thorough testing, and gets it right the first time, it can help attract new customers because you get that reputation of, hey, these guys get it right. Overall, it's going to help a shop's profitability. If you think about it doesn't matter whether you're a technician or service writer, service manager, owner, whatever, having a profitable shop is going to help everybody in the long run because at very least the place stays open and the lights stay. So always better to be more efficient and have better profitability so everybody can make more. All right. So we're going to do a live walkthrough now on the tool, talk about some of these features and functions. I know some of you may have seen some of this stuff before, but it's always good to get a refresher. And I know there's a lot of people that haven't seen this before either. So. All right, so here is my scan tool. And the first thing we want to do is I'm going to go into guided component tests here. Before I even ID a car, did you know that there are built-in classes inside these tools? A lot of folks say, hey, I want more training. I want to learn more stuff about whatever I want to learn about. Well, there's built-in classes inside the tool. Comes with it, gets updated periodically as well. So we have 3 categories of class. We have power user test, features and benefits, and how to. Power user test is going to give us some more generalized tests that are not vehicle specific, but some more generalized tests that we can do, like current probe tests, dual channel tests, secondary ignition, pressure transducer. So for example, if I wanted to do like fuel pressure test, exhaust back pressure, fuel pressure and fuel pump current on the same screen, that sort of thing, we could do that there. Dual channel tests, you can do like cam crank relationship. We're going to talk more about that next week. Flex ray bus, wheel speed sensors, multiple channels, and so on and so forth. So a lot of pre-configured tests, not vehicle specific tests, but pre-configured generalized tests. Next one's features and benefits. That'll help you if you're not familiar with using the tool. Got a 5-minute walkthrough of the demo board. Got a couple descriptions of things. Also accessories. If you walk through and you find a test that it needs, say a low amp probe or something like that, you can click on that. It's going to give you a picture and a part number. So for your reference, next time your Snap-on rep comes in, say, hey, I need a low amp probe and here's the part number. I'm sure they'd be more than happy to help you out. Then if we go back and we go to how-to, this is where the bulk of the information in here is. It's in this how-to section. So there are 65 categories of class, not necessarily even scope related, scanner related stuff in there as well. Things like start stop technology, selective catalyst reduction, pressure transducer diagnostics, NOx emissions. Let's see, running compression waveform class, right? So that talks about, that's pretty popular test. That talk about how the spikes and the ups and downs and all that good stuff. Driver assist technology, so ADAS, sparking ignition induction, all of these things. Quick little read, goes right through there. Go to basic electronics classes, right? So maybe I forgot my Ohm's law today and I need a quick refresher course on my Ohm's law, right? It's all in there, all readily available. So that is, that's pretty huge because it doesn't cost anything extra and you don't have to hook up to a vehicle to get to it either. It's just readily available, right? All right, so let's go through a couple of the basics. I'm going to hook up to my BMW demo board here. So it's 2012 BMW 328i. Pardon me, I've had this scratchy throat for a while. Different systems, ABS charging system, engine, transmission. I'm going to go into engine. And in this case, I'm going to look at a cam sensor today. We go into cam sensor and we're going to look at the exhaust cam sensor because it has both. And let's look at some component information. So we want to know how it works before we're going to go and test it. So in this case, it's a Hall effect type sensor used to detect rotational speed and position of the camshaft by interpreting a reluctor wheel attached to the camshaft. Produces a digital voltage signal pattern based on the reluctor wheel. This can be observed at the sensor. The engine control unit uses this information for fuel injection timing and cylinder identification. It's going to tell us what the component connector is, the pinouts, the wire colors, and then also if we need to test it at the PCM, possibly it's going to give it that as well. That's going to tell us where it is and where the best place to test it is. So in this case, the best place to test it is at the sensor itself, and it is located in cylinder head to the right of the two Vanos solenoids, so we can test it. All good information, all good information, because I want to know where it is. I want to know what the easiest place to test it. Go to signature test now so I can test it. It's going to tell us where to put our lead. So yellow goes to cam signal, which is going to be number 1, pin 1 right there. And then black's going to go to a known good ground. Oh, yeah, the other thing that I get asked a lot is, oh, they give us the harness, but how are we looking at it? Well, it actually tells you in there. So it says we're looking at the harness side, back probing at the component. So more often than not, if I'm going to test the component, I want power, ground, and signal applied. So I wouldn't want to disconnect it. I want to leave it plugged in. So most of the time, it's going to tell you it's harness side back probe. So we're looking at the wires as they're going in, and we're going to back probe it. So pin 1. And then it gives me a known good pattern down here. I see all the time questions. Hey, does anybody have a known good pattern for X? Do I have a known good pattern for this? Can anybody send me a known good pattern for that? Well, if you have one of these tools, you probably already have it inside the tool. So it is a good resource for you. And once again, you don't have to hook up to the car. You can just look it up, type it in, ID the vehicle, ID the engine, go to the part, and it'll tell you what it's supposed to look like. If I hit view meter though, what it's going to do is it's going to automatically set the voltage range where it needs to be, automatically sets the time base where it needs to be. And if we need it, it's going to set this trigger point for us as well. So if I scroll that up, I can see a known good pattern there. I see the pattern there. Boy, those two look almost identical. Should be a 5-volt square wave. It'll start with one short pulse, then a long square wave, and then we'll finish with a medium length square wave form and then repeat. So short, long, medium, short, long, medium. Looks good. Scope should be used to check. Now, if we come down here, in this case, it also gives us a bad example, as an example of a bad signal. We got a lot of noise going on in there. Some of the symptoms a customer might experience with this type of failure: vehicle stall while coming to a stop, vehicle would start and then immediately die. It may or may not have a check engine light or fluids. So it was captured off a live problem vehicle. So that's an example of a bad pattern right there. You see a lot of noise, a lot of hash going on in the signal. So I think that's pretty cool. These tests are built by real life human beings. They go out to auto auctions and things like that, hook up 2 components, find known goods, find known bads, put it in the database, give you all the information that you need. So it's very, very thorough amount of information in there. I think it's one of the most underutilized resources of the tool, and you can get a lot of benefit out of using it. One more thing I want to look at is going to be in the fuel system, and I want to look at the injector, because that's a pretty common thing, a pretty common failure on BMWs too. But let's look at the component information, because there's a couple different types of injectors on these. So in this case, it looks like a conventional injector, not a direct injector, not a piezoelectric injector. These are normally closed solenoids responsible for delivering atomized fuel into the intake manifold ports. When energized, the coil winding inside the fuel injector will create an electromagnetic field. So pull the pintle off the seat and allow the injector to spray fuel. Injector on time is known as pulse width, calculated by the PCM. Also tells us we're going to have constant ignition power to the injector by the fuel injector. So all good things to know. And then the best place in this case, because the fuel injectors are kind of buried, we want to test it at the ECM itself and then whatever injector we want to test. I'm going to back up. I want to do a signature test again, because we can see a lot about that injector to see how it's working. Hit view meter. Once again, it's going to set the voltage, set the time. Looks like I'm a little wider than I want to be. Change that with my simulator here. There we go. That looks fairly. So this is a known good pattern in the back here. And then this is what I got coming off my car on a simulated one anyway. And it looks pretty darn close. I will say, though, that's going off the screen. I don't know how high that is. It does preset the voltage for me, but it's set at the 50 volts. Maybe it's higher than that. Maybe it's 70 volts. I don't know. So what I want to do now is I want to change some stuff. And another misconception about this is you cannot change this as a preset, and that's just the way it is. And that is 100% not true. First thing I want to do is go up to the top, and I want to make that meter bigger. And you can do this on any of the tools that have the guided component test, not just the Zeus, not just the Varus, any of the Triton and the Modus Vantage, they'll all do it too. I'm going to come down here and open up my settings. And we have the same settings as we have in the lab. These eyeballs turn on additional channels. Like I said, we'll talk more about adding additional channels next week. If we go across, though, it's going to give us a bunch of different things. So probe is going to tell me what kind, or tell the tool what kind of probe we have in there. So test lead volts, vacuum, pressure, low amps, probe, ignition. Peak detect is going to remove any filters, any buffers, set it to maximum sample rate so you can get the little tiny details if you need them. Filter is going to set a filter on there, an RF filter in case I got a lot of noise. Inverted flips me over, upside down, right side up. It's going to be really useful if you're using a low amp probe, because low amp probes are directional and sometimes they only fit one way where you get a negative reading. So you want to be able to invert the pattern if you can. Coupling AC gets rid of the average, amplifies the difference of any signal so I can see it better on the screen. And then here we have scale. So scale is going to change the height. Remember how I talked about it being a window? This pattern is not going to change at all, but it's going to change the way it looks. I'm going to click on the scale. And in this case, I want to make it bigger. I want to make it taller. So I want to do a 100-volt range. Go to 100 volts. Now it's going 0 to 100 volts instead of 0 to 50 volts. Now we see it's just a little over 50, but it wasn't tall enough at 50 volts to see. It could have been 70, 80, 90. I don't know what it was. So I wanted to be able to see the entire pattern on the screen. And that's really the goal, using a scope, get it on the screen so you can look at it. Once it is on the screen so you can look at it, then you want to measure. The other settings we can do down here is going to be the sweep. So that's going to be here. I can change the time base I'm looking at. So I'm looking at 5 milliseconds occurring, 10 milliseconds, 20 milliseconds, and you can see how it changes on the screen. If I go to 100, it gets really small and hard to see because I'm looking at 100 milliseconds passing. If I go up to 200, I actually get another one on the screen too. So I can change my RPM. I'm going to leave it back at 10. You see I'm not really changing the pattern. I'm just changing how it looks. The other thing we can do is this trigger point right here. This trigger point does a couple things for us. First thing it does is it's going to lock it on the screen. So if I move this outside of the pattern, where'd it go? Was it coming back? Am I going to be able to catch it again? If you have a problem, getting a pattern on the screen, this trigger point is going to really come in handy. So as long as the pattern crosses this trigger point at some point, it's going to draw it on the screen from that spot. This is a pulse, so it's not a constant. So you want to be able to use that and put it inside the pattern. Just move it up and down a little bit and see if you get something on the screen. The other thing it does for us is we can drag it kind of towards the middle and move it left and right. So I want to move it over there. I want to move it over there. Where do I want to move it? That'll move the pattern kind of centrally on the screen if I want. If I want to change how it's catching it. So in this case, it's top left to bottom right. That is a downward slope or a negative slope. I'm going to catch it on the way down. If I flip that over, go the other way, it's going to catch it on a positive slope or a rising slope. It's going to catch it on the way up after it goes down. So that's all that does, is just changes it on the way up or is it on the way down. As I said, once I get it on the screen, I want to measure it. So in order to measure it, we need to put on cursors. So we'll turn our cursors on and we get these two white lines and we're going to measure it now. Now we can't measure it until we stop the recording. So I'm going to stop it down here. And then I get my measurement screen. I got to come over here to get my measurements. So you can see my measurements right. In this case, we looked at the guided component test for it and it said back probe at the power wire on the injector. So what did we say? It was 12 volt constant. So I should see 12 volt constant power with the vehicle running. In this case, I see cursor 1. Where those two lines meet right there, that's cursor 1. I'm getting 17.2 volts. That's my simulator's fault. But if it was on a real live car and I saw 17.2 volts, I would check the alternator before I did anything else. Overcharging alternator can cause a lot of different problems in the electrical system, so I address that first. In this case, that's what my simulator puts out, so we're just going to say, okay, that's fine. Next thing it does is it says it grounds the circuit to generate a magnetic field to pull the pintle off the seat. So you can see it comes down here and it goes down to ground. So if it goes down to ground right there, then we know it's opening. The circuit is pulling all the voltage through. It goes down to ground and my driver is working. Another thing you want to look out for, especially on signals that pull down to ground like this, is look at the front end. It should be pretty darn close to 90 degrees because it's showing amount of time. It's coming pretty much straight down. That's almost instantaneous. There actually is a slight angle here, but it's close enough. If you saw it come down in a curve like that, that would indicate a problem on the ground side of the circuit. It's not being able to pull down to ground fast enough. So I would indicate an issue down on the ground side of the circuit. So make sure it comes at a nice 90 degrees. What else did we learn about these? When it comes down to ground, it holds it for a set amount of time. That's called the pulse width. So what's the pulse width? I can measure time on this. So if I want to measure time, I'm going to use the white numbers down the bottom. And I'm going to put the whatever I want to measure in time base between the two. So between this and this, it's going to give me a difference. So these two numbers are just how far away is the cursor from 0. If I put it in between, it's going to give me the difference is 1.25 milliseconds. So my commanded on time of this injector is 1.25 milliseconds. So as we said, pulls up the pintle, keeps it off the seat, allows the fuel to flow. As it's holding it open, it is going to hold all that electricity in there. It's going to hold all that voltage in there. It's going to work just like an ignition coil. When the ground is released, all that voltage needs to go somewhere, so it gets induced back into the circuit. So that's why we get a spike. Let's see how tall that spike is. It's about the tallest point, 50.8 volts. 17 volts in, 50 volts out. Now, I can't tell you what known good would be on a vehicle because it's going to vary on how long was it open, how much voltage was applied, how many windings are in the coil. It's all going to vary. So it's not like they're one set known good. What you want to do is compare them across multiple injectors on a vehicle. What you want. So you can see that. And then on a real live vehicle, it would come down a lot closer. And you also would see a bump right here. You should see a bump on the way down because that is the pintle actually closing. Snapping shut gives a little bit of an extra kick down there. I don't have a good picture of it here with the simulator, but on a known good vehicle, it should have a nice little bump right there before it levels off. Goes back to what it was. So as you can see, we can see a lot of information on that circuit and how that electrically is working just by looking at voltage. You want to take it another step further, you can even add amperage to the equation too and watch the amp ramp at the same time, the current ramp at the same time it's opening. It really opens your eyes to see what's going on. If you want to see more about that, it should be in my fuel injector video. It should talk about all of those things in there as well. So that's a little overview of why do I need to test components? How do I test components? And what it should look like on the screen. So with that, that is my time for this night, but don't go anywhere. Don't go anywhere. There's a really good announcement if you haven't heard it yet that I need to make. So we are, as Snap-on Diagnostics, giving away a very epic prize. Very epic prize. So this is on any diagnostics, any Snap-on diagnostic tool that can be updated to 22.4, which is the fall release. If you have your tool running the current software at the end of the year, December 31st, as long as it's in there before December 31st, end of the day, you are entered to win one of 10 epic workstations. So we're giving away one per region in North America. If you're in the UK, if you're in Australia, sorry. I don't know if they're doing another contest over there, but this is just for North America. You will be entered. So that's like the easiest contest to enter. If you're already on software subscription, just update your tool. If you're already on a prepaid plan, just update your tool. If you need one, then you would have, just talk to your franchisee or Snap-on rep and make sure you get it installed. Some of you bought the BOGO, buy one, get one free. Just install your free one, right? So as long as you have the current software in your tool by the end of the year, end of the day and the end of the year, you will win. You could win. Say will, because it depends on how many people get software in their tool. But it's a 36-inch Epic workstation with a hutch on the top, and it comes with a Zeus Plus inside, with a docking station, with a 27-inch touchscreen on the back. Comes with all of that equipment. Retail value on that's $24,000. $24,000. Crazy. I really wish I could win one of these. Like I said, we're giving away 10 of them. It's really cool. I actually saw one without the wraps. It's really nice, big, sturdy Epic. So it's a pretty cool little unit. And 10 people in North America, that's including Canada, will get a chance to win that. It just depends. Odds are going to depend on how many people do it. We're just going to do a random drawing in early January, just to run a report, see who had it in the end of the day, December 31st. If you did, do a random drawing, maybe you win. Like I said, real easy to enter, though. If you want to know what in the world's in this software update that I'm talking about, you have one more chance to catch me live. I already have some pre-recorded ones if you want to watch those on YouTube. But if you have questions, it's always good to do it live as well. So I'm doing one on Monday, this coming Monday, 8 p.m. Eastern. It is a different link to register, or you can just watch it on YouTube because I will be streaming it there too. But if you go to snapon.com/diagwebinar-NA, you can go there and I'll tell you all about it. You can ask some questions if you have any on that as well. Next week we are talking about component testing further. We're taking it to another level, part 2. We're adding additional channels. We're going to go up to 4 channels. We're going to talk about screen and screen on some of the tools. We're going to talk about more advanced stuff that you can do with your scanner and your scope. So hopefully you can join me again. Same time, same place, 6 and 9 Eastern. Go to snapon.com/OT. You can register for Zoom. Otherwise, at 6 p.m. Eastern goes live to YouTube. If you are not subscribed on YouTube, please make sure you subscribe and ring the bell. The more people that subscribe, the better it is for me. It helps me out, allows us to keep doing these classes. We see there's continued interest in it. So youtube.com/Snap-on Diagnostics. Make sure you subscribe. The 9 p.m. Eastern goes to Facebook. So that is facebook.com/Snap-on Jason, all one word, no dash in the Snap-on. If you want to give me a follow there for the 9 p.m. Eastern. If you want to watch any of our previous topics in this series of the live stream, so we're up to 52. This is topic number 52 right now. So we have 52 episodes in there. Anything from VVT, ADOS, data bus testing, no code. What do I do when there's no code? What's my diagnostic strategy there? Any of those, we can go and you can check them out. They're all free on YouTube. So youtube.com/Snap-on Diagnostics. Once again, there is a playlist for live training. So you can go check that out at your leisure. Like we said, it's free. Now it comes up to Q&A now. Just a reminder, this is a pre-recorded session today, so I can't answer questions live, but if you're watching on Zoom, reply to the confirmation email you got, or that, because that'll go to my email box, or you can, if you're watching on YouTube, leave a comment. If you're watching on Facebook, leave a comment under the video, and I'll get to those when I return. Also want to make sure I mention my buddy Al. So he does free training as well on different scan tools. So Mondays on Apollo, Wednesdays on Zeus, and Thursdays on Triton. If you want to sign up for that free training, same time, same place, 5 and 8 p.m. Central Time, 6 and 9 Eastern. If you go to snapon.com/OT on the right-hand side of the page, you can sign up for one of his classes. Very thorough. The first hour is going to be, let's get your Wi-Fi set up. Let's get your basic settings set up. Let's get you set up on a free Snap-on Cloud account so you can share files with your customers and each other. And then I was going to walk you through code to completion on a real world scenario on Fast Track Intelligent Diagnostics. You can see how does it work? How do I work through it? And then on Wednesday and Thursday, since they have a scope and meter in those tools, I'll take about a 5-minute break and then go through the scope and meter on those tools as well for another hour. So definitely worth your time if you want a little refresher on it, or if you're new to the tool, definitely worth it. Al has been with us for a very long time, and it's definitely worth your time to spend with him. And that brings me to the end. So I'd like to thank you for spending a little bit of time, taking a little bit of time out of your busy day, come spend a little bit of time with us. Hopefully we learned a few more tips and tricks that we can use in the shop at a later date. So with that, enjoy the rest of your night. Enjoy the rest of your week. Hopefully we'll see you next week. Have a good night and take care.